Cool. Hey, everybody. My name is Richard Blakely. I work for a company called MilliCast, also a partner with Dr. Alex, who just spoke here. This is a very high-level overview of our implementation of AV1 in a real-time streaming platform, as well as some of the opportunities that come, or potential opportunities that will come for research here. Let's see if this works. All right. So AV1 for real-time broadcasting. Why? Well, the first question, taking a step back, is real-time broadcasting, why is that important in the first place? So there is latency-sensitive use cases like auctions, gambling, adult gaming, and so on, that really can't have any latency. And what people really want with that is sub-second or as real-time as possible. And there's lots of ultra-low latency use cases like 3 to 5 seconds, that sort of thing. But that doesn't work when you're trying to gamble or when something is truly real time. But then also, why AV1? Well, there's a couple of reasons, and we all really like it, obviously. One, obviously, is a higher compression rate. Especially in a platform as a service like we run, bandwidth is the #1 kind of core measurement that we build on. And so we're able to either pass the savings on to you, or while the technology is still new, we can kind of leverage that for a little while. So the compression rate is key. And one of the biggest ones also is SVC, because with traditional, well, alternative methods right now, such as the other two, they're not as efficient as this. And with being able to send all of the different bit rates in a single stream versus like ABR, where you have to do the different bit rates on the actual server, we're able to do a lot of interesting routing and take advantage of that. Of course, network resilience and simplification of the media infrastructure. A lot of the time with especially dealing with multiple bit rates, it's really expensive to do the transcoding and the mixing and whatnot. So here we have relay only, which is really good. So one of the cons here is the increase in CPU footprint. This doesn't really affect us in the live streaming world because but most of the time people doing real streaming, like gamers on Twitch or people doing actual like broadcasts, they have really powerful machines. So it's not really a big issue for us in this case. Also, the viewers are only going to pull one stream at a time. We're going to send the viewer the stream that's best for their device and their viewing. So kind of the basic smart on demand, like we like to call it, the most basic thing that needs to happen first is that the broadcaster has to send the SVC AV1 stream to the publisher node. And that usually is some sort of SFU media server type component. And then the next basic part of this is the subscriber node, which will get the stream from the publisher node and then deliver it to the viewer app. Those two things have to happen, and that's the most basic workflow for getting for the real-time smart on-demand AVR. And of course, the viewer, like I mentioned earlier, will pull the stream that's best suited for them. With the kind of the magic you start to do now is with the relay nodes. So you see them there unused. So the relay nodes allow us to do intelligent routing, so we can take the right type of stream, distribute it geographically, or whatever the edge use case is at that point. And it gives us a lot of options for efficiency. It also gives us the ability to do kind of more creative things. So the publisher node can direct the various streams and maybe can send multiple bit rates or layers from the SVC to the different subnodes, and again, distribute those to the different viewer apps based on whatever rules make sense for the use case. So let's see what else we got. So kind of in a nutshell, you have subscriber nodes, which are load-based. You have geographic distribution load-based, bandwidth, and topology. And again, all of these kind of mesh together based on the use case. You tell it what to do. But those are kind of the basic overall features of that. Now, so some other research challenges. So one thing that we cracked early on was how to scale the WebRTC stream. And that was the first research challenge. It's like, okay, like it's got to go global. It's got to be sub-second latency, et cetera, relay nodes and all that good stuff. But but what about, if you're doing live streaming, what about real-time advertising? In traditional live streaming, there's workflows for that, but in real time, you have to kind of rethink those a little bit or figure out how to do them a little differently, and also with AV1 as well. So here you see what a real-time server-side ad insertion looks like. This is what we have now with MilliCast. So you have your web app, which sends your video stream, and also, or I'm sorry, your web app or your native, whatever is the broadcaster, and also the broadcaster will trigger the ad insertion. So at whatever point the broadcaster wants to trigger the ad insertion, sends a request, goes to us through the data channel, goes to the media infrastructure here. This will go through a special node that's designated to get the ad decision. That decision comes back, and it's going to go to it's going to retrieve the ad based on the decision it made, and this will send us over an HLS or MPEG dash video. This is the huge challenge here, is the transcoder. We're going to have to transcode the HLS MPEG dash to AV1, as well as a real-time transcoding of the stream and push it into the WebRTC stream, into the SRTP stream. So this is something that Dr. Alex has been working with Intel and a few other people trying to crack, and it's possible now. So it's really cool. Anyways, that will get transcoded, and then it sends it back to the player client. So that's server-side ad insertion in real time. This is just one example of one of the research challenges that are to be overcome. There's lots of different things in the live streaming ecosystem that still need to be tackled, like real-time content protection. So this is another one challenge that we ran into, challenge or opportunity, whatever you want to call it. So there is a couple ways to do this beyond just traditional DRM. One is real-time end-to-end media encryption. Because of the double encryption through SRTP, which you can send AV1 over it. You have double encryption there. You have end-to-end media encryption. Also, AV1 watermarking there's a scientific paper that some guys I know worked on to get that working, and that essentially will send metadata that's invisible, so you can tell where the stream came from, where the rights are embedded, whatever sort of information that tells you who owns that stream or who produced that stream is in there, and that's another form of content protection that we've another challenge that we've come across. Another one is real-time recording. So it's interesting with the real-time factor. So we can record just PCAP. Gives us a few different options. One of them is you get the source packets, so you can change. You can because of SVC and the other advantages of AV1, you can replay it later at a different time and take advantage of those different things. Of course, the end-to-end media encryption support. So if you record it, it's actually stored encrypted. So if someone was to steal the file from the server, your media is not at risk. So that's another advantage of the encryption there. And then, of course, because it's PCAP, we can debug everything with Wireshark. And if there's any problem or packet loss, or you're trying to investigate a problem that happened later, which is really difficult to do in a live situation, we're able to do that there. This is the really interesting one. So a few smart people, again, came up with a concept called Narvel. Essentially, it's a no reference method of similar to VMAP, but it has no reference to the original source. So and it only has a real-time data set. So there's no like a Netflix catalog where they have all this endless data. So it really has to it really depends on a subset, or sorry, it depends on a set of data that's generic to real-time streaming. So you think about real-time streaming cases where the sub-second latency is critical, like the things that MilliCast serves, and you train it with that data. And again, auctions, for example, if you have a lot of auction data, then it's going to be able to do things very similar. And then, of course, you want to validate it on a common subset like VMAF. And you see in this diagram here, that Narvel is the same. There's really no too much of a difference, so it works really well. And then with the ultimate goal, obviously, is to adapt this in real time. So, and with that being said, Dr. Alex and I will take questions.
First, second.
Have you looked at the coding efficiency of Lib AOM real-time mode in your demo or integration?
What do you mean by efficiency?
Coding efficiency, the compression efficiency.
The compression is not is a secondary problem for us. If we cannot achieve the latency, we don't care about the compression. So we're happy to make the compromise. So we're happy if they improve the compression rate of or the coding efficiency. But for us, that was not important.
But that's true to some extent, right? If you disable all the AV1 coding tools, even if you're generating AV1 bit stream in the AV1 format, but you're not taking advantage of the AV1 coding tools, then you can run as fast as VP9, but you won't have higher coding efficiency than VP9. Then why do AV1?
I think you should ask that question to the LibAOM people.
Well, I can answer this. So on speed 8, LibAOM real time is about 15% BD rate gain compared to V9 speed 8. It's still slower, so to be fair.
Okay. I should survive.
I'll ask
Depends
you
on the next question if it's going to be nice or not.
I'll ask you an easy one. Can you elaborate a little bit more on the SVC application? I think both of you talked about it specifically. Yeah. You compared it to ABR. Are you seeing some kind of opportunities or market demand for SVC this time?
No, the idea is if you want to have real time, you have to avoid as much transcoding as you can. But if you want to adapt the viewer to the bandwidth, to the screen size and everything, you still need to have a way to change the resolution. So if you cannot do it on the server, you do it at the source. And you have two ways to do that. Either you do the multiple encryption of separately decodable stream at the source, but then all the low-level, low-frequency information is repeated across, for example. Or you use SVC, which is specifically done for that, was invented for that.
But you appreciate historically SVC never made it, and it was always an ABR, which is a multiple transcode in general for streaming applications, right?
Video conferencing SVC is used everywhere.
Everywhere, it's 100%.
So the one application where scalable video coding had success is video conferencing.
There is another reason why we want to do that. Is because if we do not have transcoding, then we can have end-to-end encryption. If you have end-to-end encryption, your content is encrypted, and you cannot transcode anyway. And so it is true that SVC has never been used in broadcast. It's not true that it cannot be successful, and we're betting that we can make it happen. I should look on both sides, or I'm biased.
Adrian's down.
Thank you. Interesting talk. I've got lots of questions. Another one on SVC. You mentioned it gives you redundancy in the face of packet loss, but packet loss is evenly distributed for bits across the wire. So if your base,
I said resilience,
not
redundancy.
Okay. But if your base layer is corrupted with the packet loss, you can't decode that or any of the dependent layers.
That's a correct statement. The advantage of SVC with respect to a single resolution or multiple encoding is that if you were to use an easy one, RTX retransmission, the frequency of your packet on the base layer, which are the only one you need to protect, can be arbitrarily long. So now instead of having to retransmit a packet every 20 milliseconds, now my time window to retransmit a packet without having an impact on the display is 4, 6, 7 times longer. So that's why it's improved. That also applied to FEC, forward error correction, and other transport. Yeah. So we can speak, that's William, right?
Yeah.
Yeah, we can speak about that or the difference with datagram on Quick if you want, which is something else we do. But that might take a little bit longer than the time we have right now.
Okay, and another question, the bits across the wire, because we looked at SVC for broadcast applications, and while it's true that your storage goes down compared to your multi-bit rate stack, your bits across the wire actually goes up. Your base layer plus your next layer is a little bit more than it would have been if you coded it non-SVC. And the trouble is that's the cost for the customer and distribution.
Right. So it depends. There is different angle, a little bit like different quality metrics for codecs. So first, there is no storage, period, in our case, right? There is no storage. So the storage cost is not there, but there is a bandwidth cost. The bandwidth cost is always present on the first mile, the sender to the ingress. But with the smart optimization, that's where all the smart routing is for, to actually make sure that you use the minimum bandwidth when you go out. And that's where you get. And you simplify a lot your internal infrastructure by having only relays. So if you take the system to do the computation on how much you gain more than you lose.
Okay. And sorry, last question. You mentioned libaOM, but where is David on real-time decoding, and have you tested it as well?
So in our case, real-time decoding, we had multiple choice, but for real-time encoding, we had only one choice. And instead of doing a proof of concept with 10 different encoder and decoder, we did a proof of concept with one, the one that had a real-time encoder, that was libaOM. Now we're testing, of course. We want to test, sorry. We're planning the test with Google and everybody interested. So I suppose Mozilla, Apple, and Microsoft will come right away. But with all the different targets. Now, David and all of that are implemented in the browsers, but not in the WebRTC stack, just on the video element stack. So there is a little bit of extra work. Niels, where are you? That Niels for Mozilla and some other people will have to do before that happens. When can we expect that in Mozilla? So that's the man for the next question.
And we've also got Ronald coming on very shortly, who can answer to David as well. So, okay, thank you guys very much.